In this video, we'll be covering Chapter 17, Section 1, which deals with the reaction process. And we're going to start off with an introduction to reaction mechanics. So, in your experience with chemistry, you may notice that some reactions take place quickly. For example, the neutralization of, hydrochloric acid and sodium hydroxide occurs rather fast. However, something like metal rusting in air takes place over a long period of time. Still other reactions, like that of hydrogen gas mixing with iodine gas to form hydrogen iodide, or 2HI, are reversible. In other words, the reaction goes back and forth and is seemingly counterproductive. And that's because these sort of chemical equations only show the actual chemicals involved. They don't dictate, how much time it takes, as well as the sequence of reactions that actually occur. In other words, it just shows what goes into the reaction over here on the left and what comes out of the reaction on the right. It doesn't show the steps that each chemical will undergo to get to the right side. In order to show the overall steps of what we're doing, we have to write what's known as a reaction mechanism, which shows, the various decomposition and whatnot that these products will undergo prior to their full transformation into the final chemical. So, for example, one reaction mechanism for this reaction right here, rather than the chemical equation, is first iodine breaks up from being diatomic into two individual iodine molecules. Next, those two iodine molecules combine with hydrogen to form the two hydrogen iodide molecules here. So as you can see, creating this hydrogen iodide from its constituent hydrogen and iodine is not as simple as this equation would make it out to be. First you have to break up the iodine, and then you have to combine it with the diatomic hydrogen. It doesn't all happen in one step. Now, like we've done previously with the enthalpy of reaction calculations, you can eliminate what are known as intermediates. Now, intermediates are basically chemicals that take place in between the initial reaction and the final reaction. So in that case, that would be the 2I. And as you can see, when you take this side minus the intermediates that have been eliminated and this side, you end up with the original chemical equation we wrote out. And this all right here is what is known as a homogeneous reaction. And that's because the reactants and products all stay in the same state. It goes from two gases combining and stays with gas the entire time. Moving on now, we're going to be going into what is known as collision theory. And collision theory basically says that in order for two molecules to react, they have to collide. And realistically, when two molecules collide, there's three possible outcomes. The first is that they collide with sufficient speed to exchange their basically elements that are attached to them and create a new compound. This is what's happening in a chemical reaction. Or they can collide and the two reactive elements can get close enough to each other but not have sufficient speed to actually react. So there's not enough energy going in, that's why these arrows are small, to break the bonds that bind this smaller element to this heavier one. Or they can have enough energy, or not enough energy realistically, but the wrong orientation. In other words, the two reactive ends of the element don't end up facing each other during the collision, and so they just go their separate ways afterwards. As a sort of real-world example, nitrogen oxide and chlorine can react to form, that should be diatomic chlorine, a hybrid as well as a single chlorine molecule, if and only if the chlorine hits the oxygen. So if you have a single chlorine atom, or let's go with a diatomic chlorine molecule, and then you have, your nitrogen and your oxygen. This chlorine will only join this group if it hits the oxygen side. If it were instead to come around and hit the nitrogen side, the nitrogen isn't electronegative enough to take away the chlorine from the oxygen. Now we're going to discuss a property of the reaction process known as activation energy. And first we're going to consider the formation of water from its constituent elements, hydrogen and oxygen, at room temperature. So you'll notice if you just had a vial of hydrogen or whatnot and a vial of oxygen, if you just mix them together at room temperature, they won't spontaneously form water, despite the fact that they have a negative enthalpy. Water has a negative enthalpy of formation, and there's plenty of Gibbs free energy, meaning this reaction could be spontaneous. And the reason that happens is it requires, if this is, the hydrogen here and the oxygen here, there's a certain energy required to break up the oxygen or give these enough kinetic energy to collide and exchange atoms. Basically right now, if they were to collide without sufficient speed, the electron clouds from the two different elements would repel one another. So, in order to get these two to react violently to create water, you have to have some sort of activation energy. And activation energy is usually represented by the symbol EA for energy of activation. Basically, you'd have, a match or flame of some sort. There's a poorly drawn flame for you. Come in and add enough energy to break up the bonds, because breaking bonds is an endothermic process. However, once you do that, the actual combination of hydrogen and oxygen will release 285 kilojoules per mole, and this should be enough energy to ignite the rest of the hydrogen and oxygen. So really what you need is this activation energy. You need just enough energy put into the system to start the reaction, and then from there the exothermic process will take over. So we've covered the change in enthalpy of this reaction previously, and we drew a plot sort of like, that, where you had the initial energy of the reactants and the initial energy of the product, and this was, the delta H, the enthalpy that was released. However, more realistically, you need a certain activation energy to get it going, and that's what this hump in the plot represents. You can see the amount of activation energy above the reactants necessary, and then the reaction will sustain itself and bring itself to, the same change in energy here from reactants to products. Moving on now, we're going to be discussing the activated complex and what exactly that means. So here we have a diagram of a few molecules in solution, let's say, and these have sufficient energy to react. Now, when these molecules have sufficient energy to react, and they're, forming new compounds due to their kinetic energy being transferred to potential energy in here, this is what is known as a transitional state of the chemical complex. Basically, it means that things are changing from one compound into another, but not necessarily with sufficient energy to completely change everything. As you'll notice, these molecules over here and over here are, just chilling around, not doing anything. But if this reaction releases enough energy into these molecules to sustain the reaction for a significant period of time relative to the length of the reaction, it becomes what is known as an activated complex. Basically meaning that a chemical reaction has been activated of sorts and is sustaining itself within the process. Now let's say we have, the activation energy of a certain reaction up here. A transitional state can occur anywhere in this sort of upward rising slope. That is, you can have some things reacting, some not. But once you get past this point of no return, if you will, where you've put in a sufficient energy to sustain the reaction, this is where you have an activated complex sustaining itself within the reaction. Now, the easiest way to do this is to raise internal temperatures, and that's done through the addition of heat to the system. And this basically just means that these molecules will, fly faster and faster, making collisions more common and thus increasing the reaction rate. And as a final cool sort of tidbit, because an activated complex contains both these initial elements, or these initial compounds rather, as well as the products over here and over here, it will express some chemical properties of both for a short time until it's done completely reacting.